as an example for the application of all the carbonyl chemistry we've just discussed, I've prepared for you the synthesis of ethinylestradiol, and that's actually one of the active components in the pill. And this drug is of course very important and has led to a lot of societal transformations in the last century, and that's why I want to discuss it here. You see, our starting material is something that involves 2 cycles, and we are having here a carbonyl group to begin with, and this carbonyl group can then act as a nucleophile, as an electrophile, together with the Grignard reagent. The Grignard reagent in this case has here a double bond attached next to the magnesium atom, and this double bond can then add in the nucleophilic addition reaction to the carbonyl component, so that we in the end up with this new component where we formed the alcohol and added our new organic fragment here to our bicyclostructure that we started with. The next step is actually the heart of the synthesis, and that's actually because it forms 2 new rings. Let me walk you through this. We are having this dicarbonyl component here again, and we see there's in the middle between these 2 carbon atoms, we see one alpha carbon that has 1 proton attached, and this proton is now very acidic, so we can easily formulate the anal form in this case here. And when we do this, the other carbonyl atom is now very likely to get attacked by some kind of nucleophile, and a nucleophile that we can find here is actually this double bond. This double bond attacks here at the carbonyl atom, and that's how we are forming the initial carbon-carbon bond, and then we are performing a further reaction cascade, so that in the end we end up here with this bicyclostructure. So you see one of the carbonyl groups that we introduce is from our second co-substrate here. The methyl group that we introduce is basically this methyl group that we are also finding here in our co-substrate, and we are also finding 2 new double bonds. This stem from the elimination first from our initial alcohol group here, and the other one is formed by the elimination of water formed by this second carbonyl group in our co-substrate. Overall, we are forming this steroid structure here. So this steroid structure is made up of these 4 rings attached in this fashion here. Now we need to transform it to end up with our structure here. Something that happens in the next step is actually the hydration of one of the double bonds, and the trick here is that only this double bond gets hydrated because we are using palladium on a calcium carbonate and hydrogen, and then we are selectively attaching a hydrogen atom only from the bottom of the ring plane, because our molecule then lies flat onto the palladium surface, and then the hydrogen is added from there. So that's why the 2 hydrogen atoms are only added from this side, because the other side would not be accessible because the methyl group sticks out from the ring plane, and then the molecule cannot approach on the palladium surface. The next thing that is happening here is actually something that we've also discussed in our lecture series, is the use of a dialcohol as a protecting group for a carbonyl component. We are using here this 1,2-ethanediol, and we are doing that to protect our carbonyl group for the next reaction step. We are doing this under acidic conditions, and in the next reaction step we are using a stronger reducing agent, in this case lithium dissolved in ammonia, to reduce our other double bond that's here a little bit more protected by 4 alkyl substituents, and by using the stronger reducing agents we can finally reduce that. Why do we need to protect our carbonyl group that we initially had in our starting material? Because lithium in ammonia would also reduce the carbonyl group to, for example, an alcohol, and then it would be gone. And we want to keep this group because it's also a part of the final product that we want to synthesize. After that, we can use diluted acid in water to again deprotect our carbonyl group. So that's exactly the chemistry that we've discussed. And then we are regenerating our carbonyl group, and we could selectively reduce our carbon-carbon double bond in this case here. Then we are doing a step that we have not discussed so far. We are using again here this pyridine based acid to deprotect our alcohol here at the end. We are having first here methoxy group, and this can also get opened up to the alcohol, because the alcohol is actually part of the molecule in the end. So, and this is then the estrone molecule that's also already active in the human body, and we can further functionalize this by using an alkene component, and we are protonating one of the hydrogen atoms here with sodium and ammonia, and then this can this nucleophile can attack our remaining carbonyl component here to also bind here, and then we are again producing a tertiary alcohol, and we are also introducing a new carbon-carbon bond between our former carbonyl carbon atom and our alkene component. And in the end, we end up with something that we then call ethinylestradiol. Where does the name come from? Ethinyl stands for this triple bond that we introduced here, and estra stems from this steroid structure that we have, and the diol is because we're having two alcohol groups attached to that. So you see the structure or the synthesis overall, although it looks quite intimidating at first, is actually quite understandable with all the chemistry that we've discussed so far. And you see that all the components are synthesized by this carbonyl chemistry that we have discussed in our course. And I think this is a nice example on how this was used. To summarize the application, we can see here these nucleophilic additions to carbonyl groups in 2 steps of the reaction. We have seen the alkene reduction in 2 steps, namely here in this step and then also here in this step. And we are forming an anol as a protecting group for one of our carbonyl components. That's also something that we've discussed. And we are having this acetal as a protecting group that I've just shown you, where we first protect and then deprotect overall. So I think this is a nice example for the application of carbonyl chemistry overall.